Just one more quick example of torque and the second law for rotation. So check out this picture. It's basically two cylinders glued onto each other, almost pictured like a battery. You know how batteries are cylindrical, but then they have that little cap on top, kind of that kind of a shape. And the little cap on top has a radius R2, which is half a meter. The main cylinder has radius 1 meter. And here are their masses also. Again, the main cylinder 1.60 kilograms, the small cap is 0.450 kilograms. And what's going to happen is there's actually two forces being applied. One force right at the edge of the main cylinder going this way, 5 newtons in magnitude. And the other one right at the edge of the cap cylinder going this way, 15 newtons. Okay, so the question is, two questions. What is the net torque? And then what is the resulting angular acceleration? This thing will accelerate rotationally one way or another unless the torques end up balancing. Okay, let's figure it out. So the torque associated with the first force. Okay, now we look at this and we notice, okay, this is perpendicular to the line from the center of rotation. And so the sine part in the torque formula is just going to be 1, because that's 90 degrees, so that's just 1. So it's just F1 times R1. And I've already put in R1, but again, that's what always goes there in the torque formula is how far away the point of application of the force is from the axis of rotation. And that's R1 here because it's right at the edge, so the full radius is where the force is being applied. Okay, so, and I'll just work out these numbers as we go so we can see them. So that would be 5 newtons times 1 meter, so 5 newton meters. The second torque is, similarly, it is perpendicular to the line that comes from the axis of rotation. So here's the line, the radius going out to the edge, and then this is perpendicular. So this also will have the sine theta being 1. And the R here is the full R2 because it's right at the edge of the cap. So this is 15 newtons times half a meter. So 7.5 newton meters. Now one other thing in this example that didn't come up before, which is these two forces, these two torques, are in different directions. Now when we say direction, we mean that rotationally. This thing can spin either clockwise or counterclockwise. And just like with number lines, with coordinate axes, we have to pick a positive direction and a negative direction. So I'll say that counterclockwise is positive and clockwise is negative. You can do it either way. That's probably the more standard of the two choices, but it really doesn't matter. And if you had torques all going in one direction, you would just make that direction be positive, whether or not it was clockwise or counterclockwise. But here I'm just going to choose counterclockwise to be positive and clockwise to be negative. And so that means my second force, so my second torque, is actually positive, and my first one is going in the negative direction. So I'm going to put that in. There we go. All right, so now the net torque will be the sum of these two. So it'll be negative 5 plus 7.5 newton meters for a net torque of positive 2.5 newton meters. So there is a net torque in the counterclockwise direction because this is positive, and that's how strong it is. All right, what is the resulting angular acceleration? So for this we need Newton's second law for rotation. It says the net torque is I alpha. Now we do have to figure out I. So over on the side here, we'll figure out I. Now we have two cylinders, and from before we stated that the formula for the moment of inertia for a cylinder, a solid cylinder, is 1/2 mr squared. Now we have two of them attached, so we're going to have 1/2 m1 r1 squared plus 1/2 m2 r2 squared. The big one and the little one connected together. You just add moments of inertia, just like you add masses. When two objects are stuck together, their masses, you just add the individual masses. Same thing with moment of inertia. Okay, so I'll just pause and then come back with the final answer when you plug everything in. And it's 0.86 kilograms meters squared. So that's the moment of inertia. Okay, so back to the second law. I'm looking for alpha. It's going to be the net torque divided by I. So 2.5 Newton meters divided by 0.86 kilogram meters squared. That's going to give me 2.9 radians per second squared. Okay, and that would be the answer there. So this battery will, if these two forces were applied, F2 kind of wins, and the thing will start to rotate counterclockwise, accelerating 2.9 radians per second.